Hello all, welcome to the second lecture on engineering mechanics. I am Dr. Aisha Zanib, Associate Professor, Department of Civil Engineering, Rajagiri School of Engineering and Technology. So, this is a brief recap on what we saw in the lecture 1. We started with the history of mechanics, the relevance, classification of mechanics, the idealizations or assumptions that we made, the basic laws which started with Newton's 3 laws, Newton's law of gravitation, equilibrium law, principle of transmissibility. Actually there is one more principle which is principle of superposition. I have not incorporated that in the previous lecture also because I am not dealing with any of our problems now, but you have to keep that in mind. Then practical applications wherein we saw resultant of forces. So, this is basically what we saw. We said the resultant of forces R is equal to square root of magnitude is given by square root of F1 square plus F2 square plus 2 F1 F2 cos theta, and alpha is given by the equation tan alpha is equal to F1 sin theta divided by F2 plus F1 cos theta. So, there is an easy way to remember the component the equation of tan alpha. You can see in the numerator it is sin coming and in the denominator it is cos. So, sin by cos is tan. So, obviously in the numerator sin should come, that is first thing. Second is alpha is the angle defined between the resultant R and the force F2. Okay. If that is the case, then in the numerator the component of F1 is coming, that is F1 sin theta is coming in the numerator, and in the denominator the other component of F1 will come. F2 will come as a whole in the denominator. Okay. And then we said this is F1 and F2, this is equivalent to a case wherein only one force is acting at an angle alpha and having a magnitude R. Okay. So, what if this is a special case of resultant of forces, that is when two components are mutually perpendicular to each other. Okay. So, what happens? What happens to this equation fx square plus fy square plus 2fx fy cos theta? Theta becomes 90 degree. Now, what is cos 90? It is 0. So, what happens to the equation? It becomes square root of fx square plus fy square. And what is tan alpha? The equation is this, and here sin 90 is 1, cos 90 is 0. So, it comes out as fy by fx. Okay. So, how did you get that? You try to construct a parallelogram, right, with fx and fy as the adjacent sides. So, when you construct a parallelogram, then the diagonal of the parallelogram will give you the magnitude of the resultant, and the angle alpha is defined by this, right. So, you can see that the diagonal of a rectangle is nothing but square root of the sum of its sides. That is what you have got over here. Now, what is tan alpha? Tan alpha is opposite side by adjacent side. How much is the magnitude of opposite side? Fy divided by adjacent side is fx. Okay. So, that is fx and so tan alpha. So, now fx and fy are known as the rectangular components of R. Why? Because fx and fy forms the adjacent sides of a rectangle. So, the parallelogram now turned into a rectangle because the angle between fx and fy is 90 degrees, right. So, we call that as the rectangular components of R. Okay. So, now another case is when two components are acting along the same direction. That means, you are having F1 and F2 both acting in the same direction. Then what is the resultant? It is given by F1 plus F2. How will you get that numerically? You have this theta is equal to 0 here because the angle between F1 and F2 is 0. Now, what is F1 square F cos 0? Cos 0 is 1. So, it turns out as F1 square plus F2 square plus 2 F1 F2, which you can write as F1 plus F2. Okay. What if it is acting in the opposite direction? That is, one force F1 is in this direction and F2 is in the other direction. So, what is the angle between them? It is 180 degrees. So, what happens here? Cos 180. How much is cos 180? Minus 1. So, that becomes F1 square plus F2 square minus 2 F1 F2, which is nothing but F1 minus F2. Okay. So, in this case the magnitude of R will be a positive value if F1 is more, and it becomes a negative value if F2 is more. Okay. And if you are getting a negative value, what does that mean? The direction is just the opposite of the direction shown over there. Okay. Fine. Now, let us consider the resultant of two forces given that 2 and 3 kilonewton is acting at mutually perpendicular direction. So, how will you get this? You will construct a rectangle, you will take the diagonal and you will put the equation R is equal to fx square plus fy square. So, that is nothing but if you put fx and fy values, you will be getting it as 3.6 kilonewtons. And then you need obviously the angle as well to completely define the force. What is the point of application is O, right. So, third quantity is angle. So, you have tan alpha is equal to Fy by Fx, or we will be getting it as 33.69 degrees. Now, let us come to resolution of forces. So, resolution of forces means you will be given R and alpha. The magnitude of R and magnitude of alpha will be given to you. You are expected to determine Fx and Fy, the magnitude of Fx and Fy. So, how will you start off? You have this R, you are asked to get Fx and Fy. So, you will try to construct a rectangle or a parallelogram, right. So, in this case it is a rectangle because it is 90 degrees. Now, what is the issue? Here you are starting from the tip of the diagonal and you are marking it up, right. There instead of that, this was Fx and from here you started constructing the rectangle. So, once you do this, this gives your Fx magnitude and this gives your Fy magnitude. So, from this triangle OAC, this triangle, what is Fx? Tan alpha, or what is cos alpha? Cos alpha is adjacent side by hypotenuse. So, you can write Fx by R. So, what is Fx? Equal to R cos alpha. Similarly, from triangle OCB, what is this angle? This angle is 90 minus alpha, right. So, cos 90 minus alpha is Fy by R, okay. So, what is cos 90 minus alpha? That is sin alpha, which is Fy by R. So, you will be getting Fy is equal to R sin alpha. So, if you have this resultant force magnitude is given as 3 kilonewton and 40 degree is the angle, then you can write Fx is equal to 3 cos 40, which is 2.3, and Fy is equal to 3 sin 40, which is 1.9 degree kilonewtons. Now, always you do not have to think or remember on this triangle, okay, OBC and OAC, it is not required. What you have to remember is, if 3 kilonewton is making an angle of 40 degrees with OA, then the component along OA will be the cos component of R. That is, Fx will be 3 cos 40 and Fy will be 3 sin 40, okay. That is how it is easy for you to remember, okay. So, whichever is the component that is making an angle with the resultant, that component will be the cos component and the other component will be the sin component, right. Fx is 3 cos 40 and Fy is 3 sin 40, okay. Fine. Now, another special case is when alpha is 0, that is when the resultant is making an angle 0 with the x axis, okay. So, what will happen? Fx is R cos alpha. What is Fx? R cos alpha, that is cos alpha is 1, which is 10 newtons. What about Fy? Fy is R sin alpha, which is 10 sin 0, which is 0 newtons, right. And what about case 2? Case 2 is this case, that is the resultant is making an angle of 90 degrees with respect to the horizontal, okay. So, in that case, what is Fx? Fx is R, sorry, this is not S, this is C. Fx is equal to R cos alpha. Now, what is cos alpha? Cos alpha, alpha is 90 degrees. How much is cos 90? 0. So, what is Fx? 0. And what is Fy? Fy is R sin alpha, which is 15 newtons. So, what do you infer from this? For any force F, its component in the direction perpendicular to its line of action is 0. For any force F, its component in the direction perpendicular to its line of action is 0. For any force F, its component in the direction perpendicular to the line of action is 0. What is the line of action? This is the line of action for this force. Perpendicular means this line, right? There is no component in that direction, okay. Fine. Now, let us come to resultant of more than 2 forces, okay. So, in the parallelogram law, you use 2 forces to find the resultant of 2 forces. What if you have 3 forces, okay? How will you resolve this? One way is to construct parallelogram 2 times, okay. You take first F1 and F2, construct the parallelogram, get the resultant, then take that resultant and F3, then construct another parallelogram, get the resultant. That is one way. Another way is, you can do it by first resolving the forces, given forces into components, and then finding the resultant by composition of those components, okay. We will see this each one step by step. So, let us consider this common meeting point as O, okay. So, what I will do is, I will draw a force diagram. How will I draw the force diagram? I will take the reference axis x and y with meeting point as origin O, here x and y with meeting as origin O, and I will use the principle of transmissibility, show all the forces 4 kilonewton, 5 kilonewton and 8 kilonewton. Okay. Now, what is the angle 8 kilonewton is making with respect to the y axis? The total angle is 60 plus 45 with respect to the horizontal. So, what with respect to the y, it will be 60 plus 45, which is 105 minus 90. So, what is that angle? 15 degrees. Okay. So, this completes the, so I have converted that hook into a particle, right, and then I have used principle of transmissibility. Now, what will I do? I will resolve these forces. How will I resolve these forces? I will take first 4 kilonewton. 4 kilonewton is already along the x direction. I am going to resolve all these forces along the x and y mutually perpendicular directions. Okay. So, if already 4 kilonewton is acting along the x direction, what is the component of 4 kilonewton along the y direction? It is 0. We saw that as a special case in resolution. Now, I will take 5 kilonewton. Okay. So, 5 kilonewton has component, one component along the x direction, the other component along the y direction. How will you do that? This is the x component, which is fx, which is equal to 5 cos 45, and what is this component? It is 5 sin 45. Similarly, you take 8 kilonewton. What is the x component? 8 sin 15, and the y component is 8 cos 15, right. So, what did you do? You converted this resultant force into two components, right. So, basically you do not need that resultant force now, that has been replaced by its corresponding components. You do not need that 5 newtons or 5 kilonewton or 8 kilonewton, you have converted that into components. Okay. Fine. So, once you have converted this into components, the next step is composition. That is, you will take the reference axis and you will keep all the forces in one common reference axis. So, I will take the force a 4 kilonewton and keep it here. I will take the 5 kilonewton, the components 5 cos 45, 5 sin 45, and then 8 sin 15 and 8 cos 15. Okay. Now, what will I do? I will take this and I will sum all the forces in the x direction. What are the forces in the x direction? There is a 4 kilonewton force, 5 cos 45, both are in the positive x direction. So, 4 plus 5 cos 45 minus 8 sin 15, which is in the negative x direction. So, minus, right. So, you add up this, you will be getting 5.46. So, that means this added up together, I will be getting a net force of 5.46 kilonewton. Similarly, you add up all the forces in the y direction, all the forces are already positive, and you will be getting that as 8.37. Okay. Now, if you have these two forces, then what is the resultant of these two forces? Square root of fx square plus fy square, which you will get as 10 kilonewton. So, that is nothing but this, the resultant. And what about alpha? Tan alpha is equal to fy by fx, which is 8.37 divided by 5.46, that is 1.53. You will be getting alpha as 57 degrees. So, that is, you have converted this into a single force 10 kilonewton with at an angle of 57 degrees. So, in effect, this was the real problem, the real life problem, where there were 3 forces acting on a hook, which you converted that into a single equivalent resultant force of 10 kilonewton acting at an angle of 57 degrees. Both has the same effect on the hook. Okay. Fine. Now, till now we saw the case wherein the effect of the force was to either to push the body or pull the body, which we call as a translatory effect. Okay, translation, the translatory effect of the force. The force has another effect, which is the rotational effect. Okay, and the rotational effect is defined by the term called moment. So, moment gives a rotational effect of the force, it quantifies the rotational effect of the force. So, what is moment? Let us consider a lever, okay, with here let A be the fulcrum and let a person be standing at a distance d from there. So, due to his weight, what will happen to this? This will try to rotate. Okay. So, this rotation is quantified by moment about the moment center. Where is the moment center here? A. A is the point which is not rotating. with respect to A, all the other points are rotating, right. So, we call A as the moment center, and with respect to the moment center, we will quantify the moment. Okay. So, I have taken moment center as A, and moment about the point MA is equal to force into perpendicular distance. So, moment is defined as force multiplied by the distance perpendicular to the line of action of the force towards the point moment center. Okay. So, this is the line of action of the force. Perpendicular means it is a horizontal direction. In the horizontal direction, from the line of action of the force towards the moment center, the distance given is d. Then I will say that moment about the point A of the force F is given as F into d. Okay, fine. Now, there is another case. What if instead of the person standing onto this side, the person is standing to this side, that is here. Okay. So, here this person was trying to produce a clockwise rotation, and here what is happening? It is trying to produce an anti-clockwise rotation. Okay. So, I will take anti-clockwise as negative. So, here I will say moment of the force about the point A is minus F into d. So, it is similar to the sign convention of x and y, Fx and Fy. You remember Fx, if it is in the along the positive x direction, we took it as positive, along the negative x direction you take it as negative. That was for the translatory effect, the push or the pull. Now, it is a rotational effect. It is rotating either clockwise direction or the anti-clockwise direction. So, if it is rotating along the clockwise direction, we take MA is equal to F into d positive. Here also the perpendicular distance is d, the force is F, that is not changed, but the direction of rotation with respect to the fulcrum is changed. So, it becomes minus F into d. So, let us consider this problem. You are asked to determine the force F so that this bar will remain horizontal. That means, the rotational effect of this 5 Newton force about the point A and the rotational effect of this force F about the point A is same. Okay. So, how will you determine that? What is the rotational effect of the 5 Newton force? 5 into 0.5, right, because 5 Newton is vertical and 0.5 is the horizontal distance. Okay. So, I will take the moment center as A because about the point A it is trying to rotate. Okay. So, I can write 5 into 0.5 is equal to F into 0.25 in the opposite direction. Both should be equal and opposite, then only it will be cancelling out, right. So, F into 0.25. So, what is the value of F? F is equal to 10 newtons. Okay. So, if you consider the effect of a force, the force has two effects. One is a translational effect, that is a push or a pull, and the second is the rotational effect, which we quantify by moment. Okay. So, what are the equilibrium conditions? What do you mean by equilibrium? The net force acting on the body is 0. The effect of the net effect of the force acting on the body is 0. So, there are two effects, translational effect and moment effect, right. So, both should be 0. Then only we can say that the body is in static equilibrium. I am dealing with statics. Okay. So, body is in static equilibrium. So, what is the net translational effect of the force? Sigma F is equal to 0, the net component along the x direction and along the y direction. Sigma F of x is equal to 0, sigma F of y is equal to 0. Sum of all the forces in any given direction should be equal to 0. Now, what about the net rotational effect as 0? Moment should be 0, right. So, if this is the case, then the net moment is 0, right. So, then if these two conditions are satisfied, then we say that the body is in equilibrium. Okay. So, that is, you have 3 equations of equilibrium: sigma f of x is equal to 0, sigma f of y equal to 0, and moment about any point O on the body is equal to 0. Why did I write sigma f of x and f of y instead of sigma f equal to 0? Because any force can be converted into two mutually perpendicular components, one along the x direction and the other along the y direction. Okay. So, it is easy for us to solve the problems with the components rather than the single force. Okay. So, that is why I have wrote like this. So, just imagine this rock. Okay. In this case, if it is trying to, we can say that it is not moving. In what sense do we say? That it is not translating in any of the directions, also it is not rotating. So, this is one of the practice problem that you can do. You are asked to determine the magnitude of the force F such that the moment produced by F with respect to A is equal and opposite to the moment produced by the 50 Newton force about the point A. That means, whatever is the moment this 50 Newton is going to make with respect to A should be same as the effect of F, the force F with respect to A. You are asked to determine that force. Okay. In the problem, instead of arrow in this direction, just take the arrow in the other direction. Okay. So, that means take this force in this direction. Okay. Let this be your force. Okay. So, what is the magnitude of force required to produce the same effect as this 50 Newton force about the point A is the question. Okay, and you are supposed to get a force of 66.7 kilonewtons.